Hey everybody, welcome to the second part of forecasting and time series. I don't know if I call it that, but it is a lot of this is about time series for the last lecture and this one. Let's go ahead and share the screen. So you probably recall that last time, this is the last thing we looked at was this forecast based on a vector autoregression. So we just went through just kind of a quick recap. So we diagnosed stationarity using ADF tests. So we talked about how that works, and then we applied that to our example of um, gas, oil, and gas price, oil price, and rig data. I'm gonna go ahead and drop this right there because we will need that for today's lecture if we ever hit go. Why? Why? There we go. So last time we just looked at the time series, which I believe I mentioned last time. If you're using time series data, like basically always number one, we actually want to do visual inspection for a variety of reasons. You may recall with the augmented Dickey-Fuller ADF test that we had to think about, do we want this is going to have a constant term, the gas price line, because the average is not zero, but it also probably does not have a trend since like if I drew a line across, it would be flat-ish. Maybe we do want a trend for oil prices. Maybe we want a trend for rigs too. We went forward with no deterministic trends, but with constants in the ADF tests because we have to make assumptions about that when we do these ADF tests. We found that none of the variables natural gas prices, natural log of natural gas prices, a natural log of oil prices, natural log of gas rigs, which are the number of rigs out in the world, out in the United States, drilling natural gas wells at any given time. The logs of those, all of those were non-stationary in levels. We saw that with these p-values. We failed to reject the null hypothesis of non-stationarity. Here, we did reject the null hypothesis of non-stationarity when we took the differences of that data. So we took today's value minus yesterday's, or this is monthly data, so this month minus last month. That difference is stationary based on these ADF tests. What we conclude from that these variables are integrated of order one, is what we say. So we discussed what vector autoregressions look like. Here is our vector autoregression system. Today we will be, and then that's what we based. So these are the errors from our vector autoregression system, and then we forecasted using that differenced vector autoregression estimation. Today we will be shifting into something called co-integration, and this aligns. I'm working on research really similar to what I'm showing you here, and this is sort of a different, and this is probably a better model for this particular series, but we needed that setup for vector autoregression that we did last time to really get into what's called co-integration and vector error correction models. So we previously found, remember that I just mentioned that all the variables were non-stationary in levels, but stationary in first differences. So then we might say these things are all of or integrated of order one, which is that statement right there. Now, when multiple integrated series move together, so it's probably true that oil prices and gas prices move together. Um, if those move together and we can make a linear combination, so what if oil price minus 5 times gas price is on average zero, and then that difference, that linear combination of the two variables, what if it's stationary? So it's integrated of order zero, meaning in levels, it would we would reject the null hypothesis of non-stationarity. If we have that relationship, we call it co-integration. And so basically, I have an economic theory based on supply and demand, essentially, which you saw earlier in the semester, that says these three variables, natural gas prices, oil prices, and natural gas rigs, should have a stationary linear combination based on the behavior of oil and natural gas businesses. So I have theory, I won't show you that theory, but the upshot of that theory is that we can say theoretically these three variables that we're using in our working example should have this combination. So when we multiply them by coefficients, because remember this is a vector of three variables, so we hit them with a vector of coefficients, and then we get a stationary combination. That's what all that this says right here. And you should recognize this is beta transpose times yt. So that's just expressing a linear combination of our variables in general and in our example. Here, yt, so the dependent variables are rk in our case, in our example, 3, but up to k. So you could have an arbitrary number of variables in your system. Beta is the called the co-integrating matrix. It's not necessarily a vector. So in my model, there's one. We produce one co-integrating vector. However, since we have three variables, we could imagine different combinations. We could have more combinations of those three variables that's stationary than just one. So we could imagine a system where our three variables have multiple linear combinations. Maybe oil and gas prices have a combination that's stationary. Maybe gas rigs and gas prices have a different combination that's stationary. Then R would be two, K would still be three, but we would have two different vectors, co-integrating vectors inside our matrix. So we'd have an entire matrix instead of just two vectors. So the vector error correction model, so what's going on here is we have one thing that we kind of call the long-term relationship. That's that co-integrating vector that might be from economic theory, usually from some type of systems level theory. But then we also have our short run dynamics. So that's essentially what we estimated last time. So let's take a look at that really quick. These equations and this one in general are all different variables, but there's no long-term relationship embedded in this. It's all just short-term changes in the variables, how they're changing over time, and how there might be dependence in that system. The difference in a VECM, a vector error correction model, is so this is essentially the same thing as before. Change in YT, a bunch of coefficients, changes in the YTs, and those are vectors. So the change in gas price can depend on the change in gas price, the lagged change in gas price, but also the lagged change in gas rigs and the lagged change in oil price. And we found that it did maybe depend on those things a little bit. What's different now is we're adding this new term. So notice here, this part is that long-term co-integrating relationship right here. So we embed that into the regression. Now, what if it's not holding? What if we get a deviation from that long-term relationship? Well, if we expect the behavior of firms or consumers or biological agents or some other system to try to shift back towards that equilibrium relationship established here, then alpha is a possibly a vector because remember there could be more than one co-integrating relationship, and it actually is a vector because there's more than one variable in the co-integrating relationship. Alpha tells us how those variables try, if they try to move back towards that relationship. So we not only estimate that long-term vector, but also what happens when we have deviations in the data from the long-term vector. And then that's all embedded into our standard difference vector autoregression from above. So this is essentially just an expanded version of the vector autoregression we looked at before, but now with the long-term relationship. And so you can just see what each of those variables are. This is going to be important. These are called the reduced form errors. And we talked about those being having the variance covariance matrix sigma, but that's a sigma k matrix, not a sigma t. It's not for every single error. It describes relationships because remember, we have a three equation system in our example. Well, there could be covariance between the error terms across equations. the individual equations have error variance. And so this matrix for us, for our three variable example, is just a 3 by 3, or in general, it's a k by k describing how errors are related across our different equations in our system. So then we can just write this guy right here. So it is sort of a first thing in co-integration is establishing that the potentially co-integrated variables are all I1, because you can't have a stationary linear combination if you have a mix of some variables that are integrated of order 1 and some that are integrated of order 0. You can work with that, but that would be a little bit outside of what we're thinking about in co-integration. So, of course, we have statistical tests to see, the main one being what's called the Johansen test. So, the Johansen test jointly estimates the system and tests for the co-integration rank R. So, it looks, do we have any of these stationary combinations of these variables in our system? So, we can choose the lag order. That's essentially based on tests we looked at before. What is the optimal lag? I guess we didn't explicitly look at them, but on our ADF tests, it's choosing the optimal lag for our system. And so if we choose, and it's important once we do var and levels, once we difference, we shift around how many lags there are. We lose a lag when we move to differences. So that's all that this is mentioning. So we also need to think about whether we have constants or trends in or outside the co-integrating space. So we might think that this stationary co-integrating vector is changing over time, but linearly. So we put a time trend in there, and that would work with co-integration. In our system, we don't have that, but we could test and compare the results across different models to see which one's better, the one where I'm using a trend or the one where I'm not using a trend. And then essentially, the Johansen procedure uses two types of statistics, trace and max eigenvalue tests across all the different potential co-integrating ranks. So 0 would mean there's no co-integration. 1 means there's one co-integrating vector. Up to, we could have one fewer co-integrating vectors than there are variables in our systems. And then we compare those to critical values. And essentially, it's a series of hypothesis tests. So we select P in this code with information criteria, which is the most common way to do it, either AIC, BIC, or HAIC, I think it is. And then we run a Johansen with a constant in the co-integration space. So that just means that there's a constant or intercept term in that co-integrating vector, because that co-integrating vector literally just looks like a regression equation on our levels variable. So in our case, it's just a regression equation with log of gas price, log of oil price, and log of natural gas rigs. So this is saying we're including an interceptor constant term in that equation. So then we essentially get our hats and we decide, okay, do we reject or accept the null hypothesis associated with this test? So let's go down here. So produces essentially a table. So these say the selected rank is 1. So it's like when we looked at the hypothesis test at 0 co-integrating vectors, we rejected that. Then we shifted the null hypothesis to 1, I think it's 1 or fewer co-integrating vectors. We accepted that hypothesis. Then we moved to 2 or fewer co-integrating vectors and we reject that hypothesis. So that's kind of how we zero in on the correct number of co-integrating vectors. So we can see here that R equals 0. We reject the hypothesis that there's 0 or fewer co-integrating vectors because our stat is less than the critical value, or sorry, our stat is greater than the critical value. This is the null hypothesis, so we reject that. However, here, our stat is less than the critical value, so we fail to reject the idea that there's 1 or fewer. So, well, if we rejected that there's 0 or fewer, but we didn't reject that there's 1 or fewer, then we say, okay, there's probably one co-integrating vector. This is simply a different type of statistic, but it shows the same results here. So then off of that basis, for moving forward, we will now move forward with the assumption that there's exactly one co-integrating vector. So now we can estimate our vector error correction model given this assumption. So we estimate the vector error correction with p minus 1 lags. And so that's based on the selection criteria that we'll use later. We then normalize the co-integrating vector so the coefficient on natural gas price equals 1 because it's arbitrary, so you can always do normalizations in the vector. And then we also report what are called the loading or adjustment coefficients alpha. Those again are the ones, if we see a deviation from the long run relationship, we should expect movement back towards the long run relationship among at least some of the variables. So we can go ahead and report and take a look at that and see, do we in fact find that type of movement? Do they adjust at all to deviations from the co-integrating relationship? So here are the results of our vector error correction model. So the top stuff is similar to what we saw before. These are all the short run dynamics. So this is the ln gas rigs equation. So this is like ln gas rigs. What does it respond to? Well, lagged ln gas rigs, it responds to. Lagged oil prices, it responds to. So gas rigs respond to both lagged gas rigs and lagged oil prices. Interesting, not gas prices. That can be completely fine in this type of a system because one of the theoretical underpinnings of this is that oil wells produce natural gas wells often produce oil. So it could be that being produced in natural gas wells, especially when natural gas prices are very low, are what attract rigs. So now we have ln natural gas price here. So this is our second equation. Here we have gas price responding to itself in the short run, but not to oil prices or gas rigs in the short run. And then finally, our oil price responds to itself, kind of responds to gas rigs in the short run, but not kind of significant at the 5% level. This one's very significant. Okay, here are our short runs. So these are the parameters on our alpha. So the coefficient so the question is, do gas rigs move from deviations from the long run relationship? Here's the coefficient, how much they move when we observe a deviation from the relationship. Yeah, super statistically significant. Do gas prices move? Yes, they do. Also very statistically significant. Oil prices, yes, as well. That is less statistically significant at the 10% level, but not the 5% level. And this actually makes sense. And this is what we expected because oil prices are more global system. And this is our natural gas prices and natural gas rigs are really within the US. So it makes sense that within the US system, our primary movers are the oil rig or the gas rigs and the oil rigs. Sorry, gas rigs and the gas prices. Well, the oil prices are more exogenous to the system because they might respond more to things like global events and respond less to the internal dynamics of this system. This is what our beta, so beta is our long run. So that co-integrating relationship, this is what that looks like when we normalize the natural gas price coefficient to 1. So this is essentially a vector that's set equal to 0. And you can move it to either side of the equation. So we could flip all of the coefficients and still maintain the validity of that. So there's always a normalization involved, or I guess there doesn't have to be, but to make sense of it, we usually use a normalization for one of our parameters like this. These are just those same coefficients that we saw here, our 0.0086, 0.0253, right there, 0.0253, and our 0.009. Those are the short run. So when we have a deviation from this relationship, if the error term is not 0, that's a deviation from this relationship. And then how do each variable change when we have such a deviation? That's what these numbers mean. And we saw that 2 out of 3 of those are very statistically significant, while this one is marginally statistically significant. So now this is really we're gonna did a lot of work to get into some more better versions of forecasting, and I think really the type of forecasting that can be really important. Um, so oftentimes when we're forecasting with systems like this, we use something called impulse response functions. So in vector autoregression and in vector error correction models, an impulse response function is just a sequence of conditional forecasts that answers the question, if a specific shock hits right now, what happens to each variable over the next right now, 1 month out, 2 months out, 3 months out periods. So we want to trace out how a shock today would go through the system. And so obviously that's relevant to forecasting and oftentimes relevant to forecasting in things where it's like, well, I'm not going to be using machine learning because I'm not trying to just get the tightest fit. I'm more trying to forecast the story. What if there's a war in the Middle East that leads to a spike in oil prices, for example? Well, that's a very out of sample thing oftentimes. Maybe we have a couple ideas of that, but maybe far in the past. A lot of other things have changed since that last war or since that last major event. So IRFs are really good for those types of environments. Just noticed, annoyingly, that some of my math isn't math, but I shouldn't be trying to fix that right now anyway. So So that's the idea behind impulse response functions. It might be really nice to say, okay, we're going to shock the system that we've estimated, and then we can forecast out how the system will evolve based on shocks. So let y hat, because it's a forecast, so it's y hat t plus h. So we're going to go h periods in the future. H could be 0, 1, 2, be the baseline h step ahead forecast at time t. And so, because we could take just the variables that as they exist today at time t, put them in the system, run the system, and make forecasts. That's kind of what we did last time. But now we want to know, okay, what happens if we shock the system? What happens if there's a shock to one of the variables, for example? So this is going to be the baseline one without the shock. We can produce that with the system. And then so we eject a one-time shock of size S. Usually this will be like a one standard deviation shock. And these are the errors. So we'll shock the error term by one standard deviation and then say what happens to the system. And so to the jth equation, so to the jth variable's innovation at time t and 0 thereafter. So we just do a one-time shock, although we could do cumulative shocks too if we wanted to see something like that. So that, and then we produce a counterfactual. So we have one path that's just based on the current estimates, but then we shock it and we have a counterfactual path. And then the IRF is a variable that just shows. So the IRF of a variable I to shock J at that horizon is just the difference between our baseline and what happened when we shocked the system. And then that's the impulse response to the shock is the difference between those two things. Because these models are linears, IRF scale with the shock. So by convention, we often use S equals 1, a 1 unit or a 1 standard deviation shock. So here the index J simply labels which shock we're talking about in our 3 variable system. So that's where my math is messed up. Maybe we can fix that right now. Yeah, it should be dollars. Ooh, sorry, I'm obsessive compulsive about that. I shouldn't be doing it in the video. Here's our 3 variable system. YT equals ln gas rigs, ln gas price, and ln oil price. So we might say J equals 1 corresponds to the a gas rig shock, J equals 2 to the gas price shock, and J equals 3 to the oil price shock because we're putting our variables in this order. So when we say a 1 standard deviation shock to J, we mean an unexpected change in that variable's structural disturbance, holding all others fixed. So now we need to think about the difference between reduced forms and structural, because structural means like there was a 1 standard deviation change in oil prices. However, we're not really ready with our estimated system, our vector system, to do that yet. So we need to think about going from reduced form because what we've estimated up here, these coefficients, the estimates of our system, our co-integrating system for our example right here is called the reduced form vector error correction model. We are not ready to yet to say, well, what happens if there's one standard deviation oil shock? We aren't ready to say that yet because those estimates are called reduced form estimates. So a stable vector autoregression or vector error correction model has a moving average process representation. So yt, any one of our variables, our vector of variables, equals a constant plus this infinite moving average of shocks. This goes to zero eventually because of the nature of these. These are a zero on average. However, that could have a large lag. It could take a long time to get back to revert to the mean, but that's what this says, is we will revert to mu in the absence of one-sided shocks in the long run. So we might say that the reduced form impulse response function to innovation J is CHJ. So we're essentially shocking this, and that's what's going to lead to a different path than the standard one, is when we observe a shock to what are called our reduced form errors right here. However, the reduced form innovations epsilon t, so these are the error terms from what we already estimated. We have three equations. We could go take a look and say, okay, these are the error terms from our equations. Those error terms will typically be correlated across equations because in the oil price equation, if a gas rig shock happens, because oil prices may depend on gas rigs, that will lead to deviations from the oil price equation. So we can't just say this shock to the oil price equation is like a one standard deviation change to oil prices because those shocks represent linear combinations of all of the different types of shocks we might experience in our system. Gas prices, oil prices, gas rigs. If any of those are shocked, we'd expect each of our three equations to be shocked. Those shocks aren't isolated. So we can't yet make statements like, what happens if there's a one standard deviation oil shock? So that's really what all of this upcoming stuff is about. We want to be able to make statements like, what happens to the system if oil prices go up by one standard deviation? What happens to the system if gas prices go up by one standard deviation, and so on? So the reduced form innovations are typically correlated across equations. To obtain meaningful pure shocks, what are known as structural shocks, we define structural shocks UT that are by construction uncorrelated and economically interpretable. And we can say it must be true that if these are linear combinations of those independent structural shocks, then we could hit them with some type of linear combination to create this sort of system. We want to find B such that we get the identity matrix when we have U prime. So this is our goal to get this, is to find a B naught basically matrix that gives us this outcome. Because once we have this outcome, then our shocks, our variance covariance matrix of shocks is zeros and ones. That means we've eliminated the covariation between the equations from the system and we've normalized each variance to one. Now we can say if there's a one standard deviation shock, what happens? And then we can say now, okay, well, there's some way to get the structural IRFs by taking CH times BO, or IRF, our impulse response function is just E prime, whatever this function is, which we need to identify E, and these are our reduced form residuals. So these E's are the observed residuals in the system. So now we need to make some assumptions to apply restrictions. We can estimate the covariance matrix of the residuals, sigma E equals epsilon epsilon prime. So that's what that covariance matrix is going to look like. That's the K by K one, remember, to distinguish from earlier in the class. And because covariance matrices can be defined over across equations now, as opposed to across observations, which we were thinking about a lot before, both can still happen here. We're focused on the former, the correlations and variation of within of each equation on our system, as opposed to every observation in our system. But it only tells us that sigma equals b naught b prime naught. For a system with k variables, sigma gives us this many known numbers because it's symmetric. But this matrix has k squared unknown elements. So we have k squared unknowns, but we have k times k plus 1 over 2 known numbers. So clearly we don't have enough knowns to identify in all of our unknown elements. So that's why we need to make some additional assumptions here to get at structural shocks. So there are basically too many unknowns to solve the system. So there's many common identification strategies. The most common is called a recursive Cholesky identification, which are called short run restrictions. This amounts to how the variables make their way through the system. So we assume some variables do not respond in the same time period contemporaneously to others within the same period. This imposes a causal ordering, a lower triangular B naught, and provides exactly the required number of zeros. Sorry, I have this, of course, again. Where is it? So the recursive Cholesky identification, we assume some variables do not respond at the same time period. So that essentially turns it into a lower triangular matrix like this. So the interpretation of ours, if we do oil price, gas rigs, then oil shocks can affect everything contemporaneously. If there's a big war in the Middle East and that causes oil prices to go up, that can change gas price and gas rigs in the current period. However, gas price shocks can affect rigs immediately. So gas prices can affect rigs in the same time period, but gas prices cannot affect oil prices in the same time period. And that's a month in our example. And then rig shocks can only affect themselves within the same month. They can start to affect the other variables later, but this is all about timing. Only oil shocks can affect everything in the month that the shock occurs. That allows us to write that B matrix, this matrix that allows us to identify structural shocks in this way. And now we have enough knowns through by assumption. We got rid of these. These are knowns now because they're zero. And so we changed some things that were unknown to things that were known, and now we can identify the system. Another one that's common when we're doing co-integration, so vector error correction, because this idea, by the way, would work in a vector autoregression, because this same issue is going to come up even without the co-integration stuff. So if we had done IRFs from last time's lecture, we would have this same issue where if we did it on the reduced form shocks, they would be mixed and we wouldn't be able to make clean statements about which variable was shocked. So we would still need to do something like this. Now, with co-integration, we can do what's called a long run restriction. We can impose restrictions on the long run effects of different variables rather than short run restrictions. So we can say, let's let C in infinity just equal the sum of these shocks right here, essentially. So the horizons. And that will be the long run multiplier matrix, which tells us how a permanent structural shocks of variables affects variables in the long run. Because in these systems, we do a shock and then variables evolve in the short run. But then how do they end up? Do they resettle in a new place in the long run, for example? Could be a question. We don't really know yet. We could, in our system, we could say in the long run, we have to expect the co-integrating relationship. So if there's an oil shock and the oil shock stays high, then those other variables are going to have to adjust somehow because that's going to shock the long run co-integrating vector in addition to the short run dynamics of the system. So this type of assumption, the SVEC structural vector error correction model long run restrictions deal with more those types of assumptions. If we believe some shocks have no permanent impact on certain variables, for example, a temporary demand shock doesn't change oil prices permanently, then we can impose those types of stricter restrictions directly. And so we can do it both ways. We can say you have to maintain this shock in the long run, or no, demand shocks go away in the long run. So this shock has to go back to zero. Both of us would lead to more knowns by which we can identify the structural shocks. So why in a vector error correction model with co-integration, of course, we have this relationship which we saw before. The term alpha beta enforces the long run equilibrium. So this is the long run equilibrium part. Remember, this is the long run equation beta prime yt minus 1, and this is the adjustment parameter for those deviations to that long run relationship. So IRFs in a vector error correction model capture both short run dynamics and long run adjustments. That's really the nice thing about this model. The long run impact of a structural shock J is the jth column of this guy. And you can, I'm not going to go deep into the math because some of this matrix math gets a little bit crazy, but I encourage you if you're interested in time series and forecasting, these are good things to know about. And then this is literally the restriction we use when applying the long run structural vector error correction identification. So SVEC and SVAR, if you see those terms, that's structural vector error correction, structural vector auto regression when we don't have the co-integration thing. So variables are in log, so IRFs are in log units. That's important to remember. To view results in actual units, we could exponentiate and do things like that. Did I accidentally put this in twice? I thought it says. Okay, that says why do we need restrictions? Why do we need restrictions? Okay, yes, this is in here twice. So I'm going to delete this. So now essentially this code is imposing those two different things, and then we're going to create impulse response functions based on everything we just went through. Oh, we have to run all because I didn't run this yet. Hopefully I put the data in here. I think I did. Yes, I did. Go, go. Oh, that went pretty quick. Okay, so this is what impulse response functions look like, and I've just mapped both of them on the same graph so we can see. So this is how, so and then what I did is I just shocked it with oil. We could shock it with the other variables too, but we just did an oil shock in this example. And so it's kind of interesting to see with our long run identified shock, this is the gas price response to the oil shock. So the gas price in the long run goes up about 2.5% and stays up. So this is a 1% increase leads to a 2.5% long run increase, and it's maintains up there. Now here we have the Koleski. Remember, that's the short run identified one, and it kind of makes sense that that one bumps, but then settles back down. In fact, goes a little bit negative. This is probably not statistically significant though. So my guess is that this one converges statistically to zero. Here's gas rig's response to oil price. So kind of as we saw before, both are increasing. So this is pretty strong evidence that yeah, oil prices do drive gas rigs to be higher from that long run relationship and apparently from the short run dynamics as well, some mix. And then here we have the oil price response to the oil price shock. We did a one standard deviation one. I didn't look at one standard deviation in oil, monthly oil. It might be about zero point 0.1. That would make sense. And then it just settles. So my guess here is that because we're doing oil on oil, we just force basically the oil shock up and it stays there. And because of the long run relationship, that maintains it. Because the Koleski, the long run relationship is playing a role in both of these. These are really both about identifying shocks. The long run relationship is part of the estimated system in both cases, though. So these are more about some other assumptions living under the hood. Again, the Koleski is about ordering. The long run identified shocks are about respecting what happens in the long run to the variables. because in these systems we always have, well, what's happening in the short run dynamics? Those have to do with like what can affect what in really soon periods. Long run dynamics are where are we going? Can we make restrictions on the long run relationship has to be maintained? And so that would allow us to say, well, as long as we know this one number, if the long run relationship has to be maintained, we can start to fill out the rest of this matrix, get our structural shocks, and get um, impulse response functions like these. Okay. So please let me know if you have a question. There's a lot here. There's a lot of rabbit holes sort of within a lot of what I'm saying, but I didn't want to spend 5 hours making the lecture. So this is really sort of a rough introduction to vector autoregression and vector error correction models. I think mixing some of this stuff with machine learning and predictive analytics, there's a lot that goes on with that, and that can be very cool. Using machine learning to identify structural shocks is something that's been happening more and more. So a lot of connections there as well. All right, so don't hesitate to reach out if you have questions about this project, anything else, and I'll see you next time.